Hello, my name is Will, and I'm a master's student here at the University of Illinois at Urbana-Champaign. I'm a part of the Reliable Autonomy Research Group, and our team is super excited to participate in the A2RL DCL Autonomous Drone Challenge. In this video, we'll show our initial progress in creating a racing drone controller for an Agilicious drone. We'll also introduce our team, discuss a bit of our strategy, and show some of the facilities available here at UIUC that can help us build a winning race drone. So, let's jump right in.
So, who are we? We are all part of the Reliable Autonomy Research Group here at the University of Illinois at Urbana-Champaign. We are advised by Professor Cheyenne Mitra, and we have a strong focus on reliable and safe autonomous systems. We've had experience in dealing with self-driving cars and other unmanned aerial vehicles. We're all super passionate about robotics and autonomy, and we can't wait to put our skills to the test in this challenge. Let's first take a look at our experimental setup. For the development of our initial drone racing system, we use the Agilicious drone platform from the University of Zurich. This is an open source platform with high thrust to weight and torque to inertia ratios for agility. For onboard compute, we use the NVIDIA Jetson TX2. This is our main computer for GPU accelerated vision processing, neural network inference, and computing control algorithms. There's a few other sensors involved on our drone. For one, we use the Intel RealSense T265 for localization. We also have an ArduCam, which is a monocular camera where we can take RGB camera images. Finally, looking at where we conducted our experiments, we're currently using a 5.6 by 5.4 by 3 meter high-flying arena at the Center for Autonomy. This space is fully equipped with the Vicon motion capture system, which will help us precisely record ground truth data. We will also have access to a much larger flying space for future experiments. Our current software architecture for the racing controller uses separate modules for state estimation, trajectory planning, and control. The state estimator uses inputs from both the vision-based gate, localization module, and an estimate from the drone's digital twin. Using these inputs and prior knowledge about the position of the gates and obstacles in the map, it generates an improved state estimate. This state estimate is used by the trajectory planner, which computes the trajectory, avoiding the obstacles and going through the gates for the drone. We use different algorithms like RRT star for generating this trajectory. The trajectory is then used by the optimal tracking controller to generate the control signals. We are exploring both model predictive control and reinforcement learning for implementing this optimal tracking controller. The generated control signal goes to both the actual drone's hardware platform, as well as the digital twin for the drone. The drone's digital twin is useful for predicting a rough position estimate for the drone, which is then used by the state estimator. The drone's hardware platform has the camera which captures the image as seen by the drone, which is then processed by our vision-based gate localization module to generate an estimate of the relative pose of the next gate relative to the current drone position. Our implementation of this architecture uses ROS, PyTorch, OpenCV, among other packages. This is one of our initial experiments, showing that the state-based controller is able to reliably fly the drone through the gates with prior knowledge of the position of the gates. You can also see the post-processing videos that we can create. For example, on the left-hand side, you can see that we can pull the Vicon data and display that so we can clearly see the path that the drone followed. On the right-hand side, you can see the RGB camera images, which we can use for gate detection, both live and in post-process. Here, you can see a more interesting example, which is our drone following a figure-8 pattern. On the right-hand side, you can see the third-person view, with the left-hand side showing the Vicon data and also the PyCam images right below it. Finally, we have an elliptical scenario with a very small minor axis to test the drone's sharp turn capabilities. Before we ran scenarios like the one you just saw, we thoroughly tested our software loop and simulation to verify our performance. On the left-hand side, you can see our RRT star planning algorithm is creating a spline-smooth path while avoiding collisions. In this case, we define an unsafe circle in which a drone should not enter, otherwise it may hit the side of a gate. Something important to note here is that there are 4 gates present in the RRT star simulation, but there are not 4 gates present in the live scenarios you just saw. This is due to a limiting number of gates that we had of similar kind. However, our drone ran on the RRT star algorithm, and therefore it performed as if there were 4 gates present. On the right-hand side is our FlightMare simulation, which is running our RRT star planning algorithm. You can see that the drone is safely passing through the gates, which helped us verify our algorithm. FlightMare and AirSim are 2 simulation platforms that we're exploring to help simulate our drone experiments. Here is the RRT start planning trajectory as well as the FlightMare simulation running on both the ellipse and figure 8 scenarios that you saw earlier. For the visual localization, gate detection, and state estimation, we're still working on testing a few different methods. As such, we have yet to factor in the vision to the state estimation. However, we have some initial progress, which we'll show here. Let's first take a look at some of the classical methods we tried. One thing that we tried was using color masking, edge detection, and contour detection to fit ellipses to the gates. Another method we tried was gradient-based edge detection and contour detection of gate patterns in the image. While both of these methods were quick and efficient, sometimes they lacked accuracy, as you can see in the videos. This leads into our learning methods, where we tried to correct these issues that we saw in the classical methods. Here, you can see we trained a YOLO V8 model to detect the gates of all different kinds. Then, we also added a CSRT tracker and a Kalman filter to improve tracking and detection of the gates. You can see that there are some performance improvements here in the videos, while there are also sometimes artifacts and improper tracking. Seeing as this is still very early stage, we will continue to work to improve and possibly unify the various methods that we've tried here. Another problem we are trying to solve is depth estimation, since it can be hard to figure out how close you are to the gate using just vision. Currently, to solve this, we're using the size of the bounding box, as well as the XY coordinates at the center of the box, in order to determine the depth, as well as the state estimation from the drone to the gate. In the graph on the right, you can see the top graph is the depth estimation, where the blue line is the ground truth data and the red line is the estimated data. You can see the same graphs for the X position and Y position, as follows below the top graph. This method is also something we will continue to expand on. Taking a step back, our research group here at the University of Illinois has developed unique and new methods for reliable vision-based autonomous control. For example, we have developed a technique called perception contracts, which allows us to design vision-based automated landing systems and also identify the safe operating design domain for the system. We regularly publish in the top venues for robotics, embedded systems, control theory, and formal verification. And our work has been covered by popular media outlets like Quanta and Wired magazines. In this recent work, titled Visual Tracking with Intermittent Visibility, we developed a vision-based target tracking controller for the Agilicious drone. Here, the pursuer has to follow the target closely, but as the pursuer gets closer and the target moves, it's easy for the pursuer to lose sight of the target. Our new algorithm has a recovery mechanism, which allows the pursuer to back off and regain visual contact, and then continue tracking. We show how switch systems theory can help design the recovery and tracking controls parameters, as you can see here. Our research is also exploring advanced control techniques for drone racing using reinforcement learning, imitation learning, and other advanced machine learning techniques like vision transformers and NERFs. This is a rendering of our drone racing arena using NERFs and adversarial disturbances, which will be used to generate robust control strategies. In addition to the flying arena, where we recorded the drone racing videos, we have access to computational resources and laboratory facilities to succeed in this competition. For example, we fly fixed-wing RC airplanes in a larger 100 feet by 40 feet indoor flying arena in the university's campus, which will also have motion capture systems installed for research in agile aerial robotics by the end of 2024. For the drone racing competition, we will perform experiments in this arena as well. Finally, I want to say a quick thank you to everyone on the team. We're all super excited to participate in this competition, and we can't wait to hear back.